In our one of our lecture, previous lecture, we defined compact space, and we gave some example of compact spaces and also some example of topological spaces which are not compact. In this lecture, we're going to discuss some of the important properties of a compact space. Let's begin with the first property. So I'm going to state first property as a theorem. Okay, so here is the theorem, or you can say this is a property of compact space, and this property or theorem, it tells us that every closed subspace of a compact space is compact. Okay, so let's prove this statement or this theorem. So let's say let X be a topological space and Y is a closed subspace of X. So here we want to show that, we want to prove that Y is compact. So in one of our previous lecture, we have described a compact subspace using open set in a topological space X. So since Y is a subspace of X, or Y is a subspace of compact space X. So to prove Y is a compact space, we're going to use open set in X. Okay. So to prove Y is a compact, so what we need to do is, if there is a covering of Y by the sets in X, then that covering should have a finite subcover of Y. So if we able to prove that one, then we can say that Y is compact. So let's say, let's consider, suppose this script A is a covering of Y by the sets open in X. So here we are assuming this script A is an arbitrary covering of Y by the sets open in X. Now to show Y is a compact, we need to show that, or we should be able to find a finite subcover of script A, or that means we should be able to find finite number of element in script A. When we take their union, it should be Y. Okay, now here what you're going to do is, this script A, which is the covering of Y, and the each element of script A, they are open in X. Now we're going to add X minus Y in this collection. So Y is, the reason is we are going to use the fact that X is compact here. So we are going to add x minus y. Y is closed, so x minus y is open because the complement of open set is closed. So x minus y, we're going to add that open set to this covering or to this collection. If we add x minus a to this collection, obviously this collection is a covering of y, and the remaining part of x will be covered by x minus y. So if we add x minus y to this collection, then the resulting collection is going to be a covering of, in fact not only the covering, is going to be an open covering of x. So consider a new collection. Consider a new collection. Let me call that the script B. So as I said before, we are adding this one more set here to this script A. Script A that covers y, and if we take the complement of y, which is x minus y, so that will cover the remaining part of x. So consider a new collection of open sets in x. Obviously each element of script A, they are open in y. This is how we have assumed, and x minus y is open because y is closed in x. So consider a new collection script B of open sets in x. Since x is compact, which given in statement, since x is compact, script B has a finite sub collection. Script B has a finite sub collection which covers x. Okay, since x is a compact, if it is compact, any open covering of x should have a finite sub collection which also covers x. Okay, but here we want to show that y is compact. To show y is compact, we have taken covering of y, which is script A, by the sets open in x. That means we want to show script A has a finite sub covering for y. Okay, so in order to find that finite sub covering of or finite sub collection of script A that covers that covers y, we almost there. So what you're going to do is, we already have a finite sub collection of x. So we're going to use that finite sub collection of x. If the this finite sub collection of x, script B has a finite sub collection which covers x. If the finite sub collection contains x minus y, then we can just discard that x minus y, because we just need the finite sub collection of y. So sorry, we just need the finite number of elements when we take their union is y. So in this finite sub collection of x, if there is x minus y, you can just delete x minus y from that collection, and the remaining element or remaining finite number of set is going to be a finite or is going to be a covering of y. That means if you take the union of those remaining element from that finite sub collection, that's gonna be y. And if there is no x minus y, then just take that finite sub collection of x, just take that finite sub cover of x, or just take that finite sub collection which covers x. That's gonna be also a finite sub collection of y. Discard y or delete y, otherwise leave the collection. If there is, in this collection, if there is no x minus y, just leave the collection alone. Okay, just let me call it sub collection alone, and the resulting collection is a finite sub collection of script A that covers Y. So Y is compact. Okay, so here we have just proved that every closed subspace of a compact space is compact. Let me give you an example related to this property of compact space. So we have just proved every closed subspace of a compact space is compact. In one of our upcoming lecture, we will prove that the every closed interval in R is it's compact. So we haven't proved this statement yet. We will prove that every closed interval in R is compact. So by using this the property that we just discussed, which says that every closed subspace of compact space is compact, since this closed space is compact, which we will prove in one of our upcoming lecture. So by using that property, the one that we just discussed, we can say that every closed subset or every closed interval in this interval is also compact. So by the last theorem, the theorem or the property that we just discussed, every closed subspace of this closed interval is compact. So this is so we use that theorem or that property to arrive this conclusion. And so this in this example we saw that every closed subspace of closed interval in R is compact. Okay, now the next I'm going to give you another property of compact space. So that property will give us a relation between compact subspace and closed subspace in a Hausdorff space. Okay, so let me state that property is a theorem. We're not going to prove this theorem, but if you are interested in a proof, you can take a look in Monker's book. And this theorem, it gives us a relation between compact subspace and closed subspace of a Hausdorff space. So here is the property or statement of our theorem: every compact subspace of a Hausdorff space is closed. So you can see the relation between compact subspace and closed subspace in a Hausdorff space. So every compact subspace of a Hausdorff space is closed. And if you take the contrapositive of this theorem or this statement, contrapositive statement is gonna be if there is a subspace in a Hausdorff space which is not closed, then that subspace is not going to be compact. So that is the contrapositive of this statement. Let me repeat that one more time. If there is a subspace in a Hausdorff space which is not closed, then that subspace is not compact. Contrapositive means if your statement is if P then Q, contrapositive is if not Q then not P. That is called the contrapositive. You guys have learned this one in in the fundamental of proof or in proof class. Okay, so as I said before, I'm not going to give the proof of this statement or this property. If you are interested in proof, you can take a look in Munker's book, but I'm gonna give you one example related to this theorem. So if you remember, in one of our previous lecture, we have seen that half open interval in R and also open interval in R, they are not compact, and we have used the definition of compact space to prove half open interval and open interval in R are not compact. But instead of using the definition of compact space to prove half open interval and open interval are not compact, we can use this theorem. We can use the contrapositive of this theorem. Okay, so let me write down that one. So basically what we have seen before is we have seen that this half open interval is not compact and also the open interval is not compact. And in one of our previous lecture, we have also seen that the real line is a Hausdorff space. Now you can see that this guy and that one, they are obviously, we are considering standard topology in R. This R is a Hausdorff space in the standard topology, and those two intervals, they are not closed. Okay, they are not closed in R. So this one, this interval and that interval, they are not closed in R, and R is the Hausdorff space. They are not closed because they are not. This is intervals are not closed in standard topology. So by the contrapositive of this statement, we can say that since these two intervals are not closed in the Hausdorff space R, so they are not compact as well. So instead of using the definition that we used in previous lecture to show these two intervals are not compact, we can just use this theorem. So by using this theorem, not directly the statement of this theorem, the contrapositive of this theorem, we can conclude that the intervals, this type of interval, like instead of fixing the endpoint 0 and 1, you can take any real number. We can conclude that the intervals, this half open interval and the open interval in R cannot be compact because they are not closed in the Hausdorff space, R. Okay, so by using this theorem, we can conclude this fact. Alright, now I'm gonna give you one more property of compact space. So in our previous lecture, we have seen that continuous image of connected space is connected, and also continuous image of path connected space is connected. That property is also true for compact space. That means the continuous image of compact space is also compact. So let me just write down that statement is a theorem. Again, I'm not going to prove this statement, but if you are interested in proof, you can take a look in Munker's book, and here is the statement of this theorem, or the properties of the property of compact space. The image of a compact space under under a continuous map is compact. Okay, that means if you have a compact space and if you have a continuous map, and if you take the image of that compact space under that continuous map, the image is going to be compact. I'm not going to prove this statement here, but this theorem is very, very useful to check. So we're going to use this theorem to check or to give the new to give a new property of compact space, or to prove the new property of compact space, and that property is very useful to check whether a continuous map is homeomorphism or not. In topology, homeomorphism is one of the most important concept. So this theorem, we're going to use this theorem to prove one new property of compact space. And like I said earlier, that property is very useful to check whether the given continuous map is homeomorphism or not. So here is the new property, and I'm going to give that property as a theorem, and here is the statement of this theorem. So let f such that x to y be a bijective continuous function. We have a bijective continuous function from x to y, and where if x is compact, and y is Hausdorff, then f is homeomorphism. So if you have a bijective continuous map from a compact space to a Hausdorff space, then that a map is homeomorphism. Okay, homeomorphism means if you have a map, if that is bijective continuous and the inverse is also continuous, then that map is called homeomorphism. So in this property, or in this theorem, our function is already bijective continuous, and in order to show that this map or this function is homeomorphism, we need to show the inverse image of f is also continuous. So we're gonna prove this statement here. Like I said earlier, this property is very, very useful to check whether the bijective continuous map is a homeomorphism or not. And the whole topology is based on the homeomorphism. That's why the homeomorphism is very important concept in topology. Okay, now like I said earlier, to show the homeomorphism, or to show f is homeomorphism, we need to show that f is bijective continuous, and which is already given. And in addition of that, we need to show that the f inverse, which is from y to x, is continuous. Okay, and to show f inverse is continuous, what you can do is, if you take the open set in x, then the inverse image of that guy under f inverse has to be open in y. That's the one way to show f inverse is continuous. And the other way, instead of open set, also if you take the closed set in y, let's say A is closed set in y, and if you take the inverse image of A under f inverse, which is the f inverse of inverse, that is the inverse image of A under f inverse, which is equivalent to say that f of A. If you show that this one is closed in y, then that's gonna be enough to show f is homeomorphism. So in order to prove f is homeomorphism, your function or this f, it has to be bijective continuous, which is already given in the statement, and then plus we need to prove f is continuous. Sorry, f inverse is continuous. And in order to prove f inverse is continuous, from this discussion we have seen that if we able to show that the image of a closed set under f is closed in y. That means if you pick a closed set in X, and if you able to show that the image of A under F is closed in Y, that's gonna be enough to show that this F is homeomorphism. That is what we're going to prove here in order to prove this statement. Okay, so we need to, just let me write down this thing here. We need to prove that the image of closed sets of X under F are closed in Y. We need to prove that the image of closed set of X under F are closed in Y to show F inverse is continuous. Okay, so let's assume that A is closed in X. So suppose A is closed in X, and then you can see in the statement X is a compact space, and we have already proved that if you have a closed subspace in a compact space, then that space or that closed subspace is compact. Suppose A is closed in X. Since X is compact, A is compact, okay, because the closed subspace of compact space is compact. Since X is compact, A is closed, so A is compact as being a closed subspace of compact space. Not only that one, since our function f is bijective continuous, f is continuous, and we know that continuous image of compact space is compact. Since A is compact, so f of A is compact. Since X is compact, A is compact, and A is compact, so that f of A is also compact, is being a continuous image of compact space. X is compact, A is compact, and f of A is compact, is being a continuous image of a compact space. Okay, now here if you go back to this statement, you can see that Y is a Hausdorff space, and then we have just seen that f of A is a compact space. Okay, f of A is a compact space in Y, and Y is a Hausdorff space. And one of our property that we discussed earlier, that property, it tells us that every compact space of a Hausdorff space, or every compact subspace of a Hausdorff space, is closed. So that we can conclude that since Y is a Hausdorff, that is given in this statement, and we have just seen that f of A is compact. So every compact subspace of Hausdorff space is closed. Since Y is Hausdorff, which is given in the statement, since Y is Hausdorff, and f of A is compact subspace of y, we can say that f of a is closed because the compact subspace of Hausdorff space is closed. Okay, so we have just proved that the image of a closed set A under F is closed in Y, and thus F inverse is continuous. Okay, so we have a map F from X to Y from a compact space to Hausdorff space, which is continuous and bijective, and the inverse is also continuous. So that F is homeomorphism. So this property is very useful to check whether the bijective continuous map from a compact space to Hausdorff space is homeomorphic, is a homeomorphism or not. Now that's all for the proof of this statement. Now I'm gonna give you one more property of compact space as a theorem. I'm not going to give the proof of this theorem, and if you are interested in proof, you can take a look in Munker's book. And the property or the statement of this theorem, it tells us that the product, that means is the Cartesian product, okay, the product of finitely many compact space is compact. So if you take if you have a finite number of compact space, and if you take their Cartesian product, the resulting Cartesian product is also going to be compact. Okay, there is one more thing, then we done with this lecture. So the next I'm going to give you one more definition. Let me write down this definition. This is the definition for finite intersection property. Okay, so here is the finite intersection property or definition for the finite intersection property. A collection is script A of subsets of a topological space X is said to have a collection script A of subset of X is said to have the finite intersection property, said to have a finite intersection property if for every finite subcollection of a script A, let's say the one is A1, A2 up to AN. Say this is the subcollection of a script A. If for every finite subcollection of a script A, let's say that subcollection is those of n is A1, A2 up to AN, the intersection, if you take the intersection of those n elements of script A, the intersection must be non-empty. Okay, it's non-empty. So if you have a collection of subset of given topological space, and that collection is said to have a finite intersection property, if you take any finite number of elements from that collection, and if you take the intersection of those finite number of elements, and if the intersection is non-empty, then that collection is said to have a finite intersection property. Okay, now let me give you example here. So here is an example of a collection which has finite intersection property. Okay, consider the collection consider the collection of open intervals. So our topological space is a real line with the standard topology. Consider the collection of open intervals, and let me call that collection is script A, and here's the collection is 0 1 0 1 half 0 1 third, and then 0 1 4, and then keep going. So you can see in each interval left side is a 0 fixed but is not included, and the right side is the reciprocal of positive integer. Consider the collection of open interval. Then script A has the finite intersection property. This is because if you take any finite number of elements from this collection and if you take their intersection, the intersection is gonna be non-empty, because let's say those finite elements are first n intervals of this collection, which is 0 1 0 1 half 0 1 third, and we are taking their intersection, and let's say the last one is 0 1 over n, then obviously this one is non empty. So you can, which also you can see from this graph, this is on positive infinity side, this one is negative infinity, we have 0, we have 1 here. So our collection are the intervals between 0 and 1, okay? And so we are taking the, so this is our first one, and the second one is 1 half, and the third one is 1 third, and the fourth one is 1 4, and you keep going, and the last one is gonna be 1 over n, and when you take the intersection of all of them, then this part is their common part. So since this is their intersection part, so is non-empty. That's why this collection has the finite intersection property.